I'm super happy to present Dean's thesis seminar on predicting fine finger motions. So this is work that Dean has been doing with a lot of advisors and very little advice, I guess. So he managed to gather around himself a group of people that can give small advice, and he manages to consolidate all of this and bring it to the next level with a lot of independent work and a lot of vision. And you'll see it throughout this talk. So I'm super excited to hear this seminar, and I hope you enjoy it and be inspired of what you can do when you don't see walls, but you see opportunities.
Thank you, Oren, for the lovely introduction. Hello, everyone, and thank you so much for coming over. So I'm going to start. This is the name of the thesis, Towards Predicting Fine Finger Motions from Ultrasound Images via Kinematic Representations. And we are going to start with some background around what we are trying to do and what we are focusing on. The background is basically robotic prosthesis and the way people are challenging tasks all around the world. According to what we know these days, there are more than 1.7 million people with limb loss in the United States only. There are no accurate numbers regarding the entire world. There are high rejection rates among users for electronic devices. What people mostly have here is that some of them have mechanical devices that they can just put on their limb and maybe grasp or touch stuff. And there are electronic devices that are using a technology called electromyography. We'll talk about it a little bit. And the rejection rates are among 1 every 2 people. So people are still working hard on the task. And we know, according to some studies, that if there will be technology improvements, more than half of the people will want to try them and go back and reuse the hands that they were using. So what is electromyography and what people were trying to do since, I guess, World War II is to take a sensor that is worked by placing a sticker on top of the skin and detect the electric potential that is generated through the muscle. What it means is that where a person, right here, you can see this one putting an EMG on his limb. And what it does is that when you flex when you just take a grasp, it detects that you're trying to use force, and we can operate a robotic prosthesis to perform grasping and leave it back. So most of the solutions currently available on the market cannot do more than grasping or gentle grasping, which is mostly pinching. And people were trying to do more than that with a more sophisticated solutions. What people try to do more is to use multi-unit electromyography, in which using this sensor, what they have is more than just a single dimensional signal. They have a multidimensional signal, which allows them to do much more than just grasping and leaving back the hand. As you can see here in 2019, people try to do multi-class classification, in which they're trying to differentiate between different gestures. And researchers already built low budget prostheses that can be used with this technology in order to actually provide it for people that in need, as you can see here, how you can actually put this bracelet on top of the residual limb. So the techniques are mostly machine learning based techniques. People are gathering data and they're trying to use classifiers to perform linear discrimination and other technologies. What it can do is that it cannot currently, and at least in the best way, they cannot reconstruct continuous movements and gentle movements. So what's the alternative? What people are trying to do since, to the best of our knowledge, since 2015 is to use ultrasound instead. Now, the idea here is basically, instead of taking the electric potential that is generated through the muscle, we are trying to take the image from the muscle as a state. and understand what is the relation between the state of the muscles and what our fingers are actually doing. So people started by gathering images and performing gesture tasks. And one of the beautiful things they were seeing from the first moment is that we can actually differ between flexed fingers. What wasn't possible in electromyography is that now we can understand which of the fingers are being flexed at each time step. So as you can, the machine learning people can already understand here that instead of taking the single dimensional signal, people were doing downsampling to ultrasound images, extracting the features such as motion or other correlations, and built algorithms that can understand to create the mapping between the fingers and the images. So, and also already been shown in 2018 that it's also work on amputated people. So what we were trying to do is that we realized that if people already realized how to differentiate between fingers, that maybe if we can have a high resolution ultrasound sensor, then we can actually reconstruct the continuous movements and the gentle movements. So we decided to concentrate on 2 case studies. Both of them were not researched till today, to the best of our knowledge, of course. And they are keyboard typing and piano playing. In these 2 tasks, we are trying to understand what exactly the hand is trying to do in real time. And this is what we're going to talk today. How do we do that? So before I start talking about the approach, just a small preliminary about what is it and why is it working. What you can see on the left is a cross-section image of the lower arm, manually labeled by a doctor. And you can see all the muscles. Here you can see the 2 main bones, the flexor muscles and the extensor muscles. Flexor muscles are in charge of flexing the fingers, and the extensor muscles are in charge of extending the fingers and creating this gesture that we are trying to do. What you can see on the right is an ultrasound image taken from our sensor, manually labeled by us. And you can see here that we can actually see all the muscles in charge of flexing from one image. And we will show that it's enough to understand exactly what are the pressing motions that the person is trying to do. So what are we trying to do exactly? Instead of differentiating between gestures and understand exactly which of the gesture the person is currently trying to do, what we want to do is that we want to reconstruct the entire motion of the hand by just looking on a stream of ultrasound images. The idea is that if we can have a lower dimensional representation of the hand, such as a configuration space, just as we have in manipulators in robotics, then we can create a better reconstruction of the hand, create better motions. And by reconstructing these motions, we can understand tasks that were not researched before, just as the 2 I presented in the first slide. So what do we mean by robotic hands and how do we construct this configuration space? It will be right away. But first, what is important to mention is that in order to understand exactly what's the state of the hand, the robotic state of the hand from a single image, the best way to do that, as we were seeing in our experiments, is that to learn the dynamics of the hand by taking a sequence of robotic states out of a sequence of ultrasound images. By building a model that can understand the dynamics, not only a single state from a single image, the model can be more accurate and understand much better the task that we are trying to do. And it's important to mention that the end goal is to create an event task, which means that where we are trying to do what we are trying to do, we don't want just to get the motion of the hand. We want to get the events that are performed by the hand. So piano playing and keyboard typing, for example, can be defined as key pressing events. In these key pressing events, we are trying to understand exactly when the person pressed on the piano and the exact time steps in which he used his finger back and put it up and leave the keynote. So the learning the dynamics is also being incorporated into these tasks as well. And what we are trying to do here is that we are trying to do both. What do we mean by that? If we have the reconstructed configuration space of the hand, we can use it to create better tasks. So instead of directly learn the key pressing events, what we want to do is that we want to use the robotic states, the hand configuration, as an intermediate representation, just as has been used in deep learning for many other tasks. But in this place, the intermediate representation will be something that is robotic specific. And we will show that this idea is actually creating the best results we can have. So just a bit of formalism before we get into the experiments themselves. We will denote the ultrasound images as it will be a single image. The sequence of K ultrasound images will be as bar of SL, and will denote a vector of K images. In similar to the images, we have our key pressing events. So to define better what's a key pressing event, we have 5 fingers from F1 to F5, where F1 is the thumb and F5 is the little finger. The vector indicating the finger pressed at each timestamp is a binary vector, but listen to that, it's not a one-hot or a null zero. It's not a one-hot vector. It can be a null zeros, it can be all ones, because we want a vector that can model a state in which a person is pressing at 2 fingers at once. So the PJ will not be, it will be a binary vector, but it can have a multiple number of ones as well. So if PJ or in time step, if PJ of finger I is 1, it means that FI is currently pressed. And if PJ at time step I is 0, it means otherwise. It's currently, the finger is not pressing the key. So we will take these 5 variables, and this is what PJ is. And again, it's similar to what we did in the ultrasound images, the bar of P of L will be the sequence of K pressing vectors. So if K is 8, and here we have 5 values, this is basically a vector of 40 values. And here we will just denote that predicted values will be a hat of P of L. And in the same way, we will create a configuration. This will be denoted by X. And again, the vector itself will be bar of X, and the predicted will be hat of bar of X. Now, what's the configuration itself? This is actually what we were doing. It's important to mention before we dive into this that the hand has a few degrees of freedom that are not incorporated into this configuration. What we have here is that the thumb has 2 joints, one for the main joint and one for the secondary one. Each of the 4 fingers have 3 joints each. All of them are related to flexing. And the wrist itself has its 3 degrees of freedom denoted with 4 PTO. So the configuration of the hand is basically a vector of all these 17 joint angles. Now, I would like to say that this is a task-specific configuration in which, if you take into example of adjacent fingers, we have the abduction muscles that perform this horizontal movement, then it's not incorporated into this, into the hand that we created, because when we want to reconstruct finger pressing, we want only to detect the flexion of the finger. So this is why we use these 17 joint angles. And now for the objective itself. So what do we need in order to take this and make a deep learning model out of it, a machine learning process, is that we need to create a model that can take these images and do this reconstruction. And unsurprisingly, the simplest way to understand it is also the best way to do that. So it composed of 2 main stages. First, the convolution blocks will be held in order to extract the features and learn the features from the ultrasound to create a lower representation of the image for each of the timestamp. And then we will use a recurrent block, which means a sequence of recurrent layers. I won't go through how LSTM works here, but all you need to know is that these are layers related to neural networks that their role is to take into account the extracted features and share the knowledge between the stage such that each timestamp understand what happens before and what's currently happening right now. And this is why we believe this model actually worked better than just understanding one single image. So we have here, and this is how we get the predicted trajectory of hand configurations. And if we take all this architecture into one encoder, then our objective is as simple as that. All we want is a mean squared error between all the joint angles in the sequence. And this is how we train our model. So in deep learning, we want to construct a loss. This is the loss. Now, what we are doing here is that we are only training the encoder to understand the movements of the hand as I explained it before. But what we're going to do now, and in the next slide, is that we're going to take these weights of the encoder as pre-trained weights and use it to pre-train a higher model. So what's happening here? It's as follows. This was already trained to understand the movements of the hand. Now, what we are trying to do is that we want to add a decoder to understand the events themselves. So the decoder is similar to the recurrent layers that were instructed that were composed by the encoder. But here, what we do is two things. We let it have the reconstructed hand configurations as input, and we add a residual connection so the decoder will be aware of the state of the muscles as well. So in here we have a decoder that is trying to understand which are the keys that are being pressed at each timestamp by having both the motion of the hand and the motion of the muscles themselves. And the objective, it looks scary, but it's not that scary. It's actually much more simple than it looks like. It's just a linear combination between two objectives. The one that we talked about just now, about reconstructing the joint angles, and the other one, which is a binary cross entropy on the key pressing events. Now, why are we using binary cross entropy? Those of you that are working on machine learning probably already realized that when you want to do something that is similar to classification, but we also want to allow the state in which all the probabilities are zeros or a few or a few probabilities will be ones as well, then we want to relate to each of the probabilities independently. And thus, this is why we use binary cross entropy. So each of the outputs here will understand better exactly what the figure is trying to do at each time step. And this is actually the objective. As you can understand here, the output of this entire neural network is just creating the key pressing events, in which the idea is that where we put a sensor on top of our lower limb, the work of the model is basically to infer in real time the music that is being played or the text that is being typed by the same hand. So from here on, I'm going to go through the setup and talk about experiments. So how did we perform the setup? We acquired a dedicated wireless ultrasound device. This is a high resolution imaging ultrasound that is also wireless and can be fixed to some place on the body without having any wires in it. We used the Vicon motion capture system to extract the exact location of each of the links of the hand palm, in which we used in order to extract the joint angles that we need for the hand configuration. And we used two devices, a digital piano and a digital keyboard, to record the key pressing events. How the setup looks like is that by 3D printing a dedicated bracelet for our ultrasound, we can fix it on the lower limb, exactly where the flexor muscles are being found. And while the person is playing or typing a keyboard, all the systems simultaneously record all the devices we need in order to create a data set. The final data set including 12 amazing subjects who volunteered for the experiment. And it's approximately 45,000 samples for piano playing and 42,000 samples for keyboard typing. And of course, this data set also will be published publicly soon. So what was the results and what was harder and what was less harder than we thought? So first, training. How do we train it? It's just important to give the technical details. The images were downsampled to 200 by 224 resolution per each dimension. Of course, normalization as simple normalization. The CNN block I showed before was based on the encoding part of UNIT. Why did we use UNIT is from the same fact that UNIT was the state of the art in biomedical imaging back when it was proposed. So we just took the encoder part of it to get the best features that we can get from our ultrasound images. K, the number of samples in a sequence is 8. We'll talk about more why. And the value of lambda, which is the factor of the linear combination between the two losses, it was chosen using a trial and error procedure. And what's important to say is that the evaluation was used using 5-fold validation. So to make it fair between all the subjects and to have the averaged results for each subject in the honest way, we took all the sessions of all the subjects and divided them into 5 folds, in which we are using 5-fold validation, which means we train on 4 folds and put 1 fold aside and repeat the same process with the next fold and average everything. So the results will be fair. And what we saw evidently is that an interesting thing that was, first of all, what did we compare with? So CBMF model is the model that I presented you, is the main objective. MF is the same model, but taking only the encoder without the robotic configurations and trying to predict the key pressing events directly. And SF is a single frame model, which means doing the same thing as the multi-frame model, the MF, but with 1 single image, and that's it. And the first thing that we noted was that we couldn't basically predict keyboard typing without having the dynamics of the hand. So by having only 1 image as an input to the model, we couldn't understand the text that was typed by the person, which was interesting to see that the movement was so subtle and not visible to a human eye that only a deep learning model that was able to learn the dynamics was able to do it perfectly. And the next thing was that you can see here is that the loss of the CBMF model starts from a much better starting point. And we believe that is due to the fact that pre-training on the robotic configurations was so close to the end task that the prior knowledge that was given from the robotic hands, from the robotic motion, was good enough to create even better results in some way, even before the second epoch started. So why did we choose 8 images? We also experimented different sequences of images, and we saw that it's gradually getting better the more images we are adding. But there are a memory trade-off, and we can't use more than we want to. And with a single desktop GPU, if you want to work with devices that are related to real time, then 8 images was the right amount in which we could put in 1 GPU. So it's important to say that it might be even better with better compute. Now, metrics. What you can see here is that accuracy, recall, and precision, and F1. As you can already see, accuracy is not that informative from the simple reason that when we detect finger typing, a lot of the probabilities the ground truth is 0, so there's not much to do about it. But recall and precision are interesting because we want to prevent false positives, especially when a person typed on a place, or especially when the model predicted a place that was typed and the person didn't do that, or if the model missed a place that was typed by the person, then we want to construct a better predictions and make the model much more consecutive than we can do. So what you can see here, and that was interesting to see from the beginning, is that piano playing is much more easier than keyboard typing. And to our opinion is due to the fact that the offset that is being performed by playing a piano is longer than the offset that is being performed by typing a keyboard. And that if you create a typing motion that is longer than the other, then the model will understand it much better. So in piano playing, you can already see that even in single frame, we had pretty good results, but we still had improvements for using the multi-frame and instructing the robotic configuration. But you can see that in keyboard typing, a task that was much harder, recall and precision are significantly better from using the robotic configuration instead of using only the multi-frame. And what we saw is that the main reason for that is that the model is being much more consecutive, and I will show it to you later on, in predicting exactly the time step in which the finger started to the pressing event and the finger was left behind. So let's go on to a few more comparisons, which we thought it were important to show. The first was the subject comparison. How good is it for a large group of subjects? Part of the main challenges in deep learning is generalization, and how can we use a model to work on a large group of people. And it was important to see that although this method is work in a good way, we have to say, on all of the 12 subjects, it can be seen that most of some of the subjects are much better than the others. We believe that it's related mostly to the motion and the activity of the muscles, and of course, the size of the muscles. But it's still, the nice thing to show is that even for keyboard typing, we were able to get good results for all of the subject, which was much more encouraging than we thought. And with regarding the fingers themselves, then what we can see here is that the 3 middle fingers work better than the thumb and the little finger. Our reason for that, what we thought is that the fact is that the muscles that are in charge of the little finger and the thumb are smaller and less significant in their motions in the ultrasound, especially the thumb that is being connected to a different muscle called the FPL, which is smaller in our cross-section image, and it's harder to the algorithm to detect it. And especially the little finger, just because the motion itself is more gentle, despite being connected to the same muscles. And this is why we think that this is the reason, at least to our opinion, why it's less good than the others. But an interesting thing to see that the little finger is still working much better, and the thumb as well, in piano playing rather than in keyboard typing, which might imply the fact that if we perform longer pressing movements, we can even improve the less tougher fingers. So about estimating configurations, it's a bit hard to see, and I will show a small demo about it. It's a bit hard to see how an estimated configuration looks like because the motions are really gentle, and from a human observer, it's hard to understand exactly where the motions are okay and where the motions are not okay. But what you can see here is that we collected the data from the average error in both tasks, and it probably looks like that the more the task perform longer movements, then of course reconstructing the configuration is harder and the error itself has a larger variance. But we are still getting that the results are, that's in radians, in average radians, the results are still pretty good in our opinion. So just to let you understand better what's the differences between using a robotic configuration and not using the robotic configuration. This is the multi-frame model. This is the configuration-based multi-frame model. This one is the one that we propose in using the robotic configuration. And this is the ground truth, meaning this is what we, the system itself is recording. Now, what you can see here is that each of the rows is a different finger. The highest row is the little finger, and the lowest row is the thumb. So basically what is being happening right now is that the person is playing a piano. He's using his index finger, and then he switched to his thumb finger. And it's hard to see exactly the differences, but for the sharpest eye, you will see that the FPL around here is being different until the end, from the fact that the person left his thumb up, and I'm sorry, for the time that the person flexed his thumb after leaving his index finger up. And you can see here that the configuration-based model was able to understand better the first occurrence of the pressing motion of the thumb. So this is only one example of what is happening. Another example in keyboard typing, and it's something that we saw a lot in a lot of the samples, is that in both in the beginning of the pressing motion and at the end of the pressing motion, we have faulties and mispredictions of a model without the configuration without the configuration to understand exactly the motion duration. In our opinion, the reason for that is that when you have the additional knowledge of the robotic configuration, you can understand better the position of the finger. Because for those of you who took Introduction to Robotics and other courses, you can understand that if we have the links and the joint angles, then we can have the precise location of the finger. So we believe that the knowledge incorporated from the configuration and what the model learned about the person itself is what causing the configuration-based model to perform better. So a few demos, just to sum up. The first one is something that we did in the beginning of this research. It's not showing key pressing motions, it's showing a much simpler motion, which is finger flexing. You can see here the ultrasound stream from a test set and what the model is trying to predict. Blue is ground truth and red is predictions. And what you can see here is that when the model have a good prior knowledge regarding the subject, then it's much easier to reconstruct the entire motion. That you can see a few faulties here. You can have the little finger being left before the ground truth, but the motion itself is still very accurate, as you can see, and it doesn't confuse between fingers, which is great to our opinion. And you can see here what the motion looks like on flexing. Now, since the motion is longer than key pressing, you can see that the motion itself is longer and much more intuitive. And I can tell from my experience, even from my human eye, it's easy to understand exactly just from seeing it, which one of the fingers is currently being flexed. But the most interesting part is how do we construct piano playing? And in this demo, I can actually show you exactly, can actually show you exactly how piano playing is being reconstructed. What we did here is just to connect the model to a simulation that will play the piano music. And you can see that the motions that are more prominent than keyboard typing, but are much less observable than flexing the fingers. If we take our model that also incorporates the dynamics and robotic motion, the piano playing is pretty good. Of course, this is only one finger. I'm sorry, this is only one hand and only 5 fingers, but the potential to have a better movement and better music from understanding the position of the hand itself is not limited, and we believe in that it can be happening in the end. And that's it. Now, for future work, there are so many things to do right now. We are interested in a few main applications. Of course, one of the things we didn't show here is how do we understand motion from a person without a prior knowledge regarding the person itself. So the test set involved people that were part of the train set as well. And even current solutions in the market use calibration in order to understand the person before he start to use his hand. So one of the interesting things to try is to understand if we can create algorithms that can understand emotion without even know nothing about the person. That's for the start. Now, other stuff that we want to do is that we want to take it just not into typing, but we want to concentrate in better tasks. And we believe that using the interpreted representation for robotic configurations can also help us to understand better multitask prediction. So if we have a person that we can understand the robotic configuration of the hand while he uses a robotic prosthesis, then maybe we can detect better the task that he's trying to do by just looking on the predictions we are trying to deliver. This is one of the things that we're doing. And of course, going into the clinical applications for people that have their own conditions, what we believe is that it's so important to address these technologies into the medical applications. There are people with neurological conditions that in need for sophisticated exoskeletons that will be executed digitally and fix the motions. Of course, robotic prosthesis is still a place in which there's so much to do in order to make people more happy with the hands that they have. And another example that I want to share is post-stroke symptom in which people are losing the way they can extend their fingers. And this is a nice example from a group called Haifa 3D that are working for providing 3D printed solutions without cost for people in need. And they built a glove that can actually extend the fingers. So there's a lot to do in terms of perform active fixation of the movements for a lot of neurological disorders. So that's it, guys, and thank you for listening. I would like to thank, of course, to the 3 amazing labs who supported and funded this research, the BRML by Professor Wolf, Vista by Professor Bronstein, and CRL by Professor Salzman, and of course, Haifa 3D for the ongoing support through this research and what they're doing so far to provide 3D printed heads for everyone in need. It's important to mention it. It's really an interesting thing to see. If you know anyone that is in need for some solution, please make him in contact with us. And there are people that can help. Thank you, guys.
Dean, do you hear me? This is
Hi, Olav. How are you?
not good. But anyway, have you tried encoding it into this music transcript that you can play automatically? Just forgot the name.
Yoav, we are having problems of hearing you.
Really standard for digital music. Basically, that encoded notes.
I'm sorry, I didn't
Certainly.
understand the question. Okay.
There is
Can
an
we-
encoding of music that you take the notes and you can take on automatic piano. So you could translate your data into that code. And then
mean-
have a demo that plays it automatically.
I think it's exactly what we were doing. So the system itself record the exact MIDI messages that are being taken from the piano. And the model is only in charge of deciding which of the fingers are being pressed. So we did use some mapping between the fingers and the accords that they are being placed below the fingers in order to create a simulation.
I'll send you a link.
I hope I answered it in the right way.
Do we have any more questions?
Can this system perform in real time? Or what is the bottlenecks?
Great question, and thank you for that. So we were just starting to work on a robotic system that will be used in real time. Theoretically, the system can be performed in real time. The model is being operated in a frequency of 60 hertz, and the ultrasound is being processing images in a frequency of 20 hertz. So it's possible. What we are working on right now is to deliver the model into an embedded system that will be connected to a prosthetic hand that we developed in the biorobotics lab. In the biorobotics lab, we have a prosthetic hand that was made from low-budget sensors. And the next step will show that it will work. But I can already say that it theoretically can work.
Great, thanks.
Thank you.
Can I ask you a question?
Of course.
Very nice work, first of all. Two questions, actually. Sorry. The first, how sensitive it is to the location where you put the ultrasonic probe? I guess you get different anatomy at each location. Did you check that out? The second question is, how do you envision a practical, possibly future application on daily life?
Thank you, Professor, for the questions. It was interesting to hear it from a perspective of someone who works mainly on ultrasound. So yeah, it's true that the algorithm is sensitive to location. And when taking a small amount of what we call placements of the ultrasound for each people, it's not enough to understand when you disconnect and place it back. So we believe that two solutions can be made. One is just to collect more data to have a better knowledge about the sensor's anatomical structure. The other is maybe to add more information regarding the placement of the probe while we constructing the predictions themselves. So yeah, so it's not just the placement, it's about how tight you stretch the bracelet and everything. Of course, it can affect everything. And what I see in the future is that the ultrasound that we acquired for this is currently the state of the art for such a task, but in the future, and especially due to the rise of ultrasound on a chip and recent technologies that allow more ultrasound elements into a sensor with having less, with consuming less power and being and way less. We believe that in the future we are not far away from the day that we will have bracelets with imaging that we can use for such a test.
Thank you.
Thank you.
I also have a question if we still have some time for it. First of all, thank you for the talk, Dean. It was very interesting. Something that I recently discovered relating to that that not necessarily all people have the same degrees of freedom in their fingers. Specifically, what I mean is that I can mostly move my little finger independent of my ring finger. Recently, I discovered that this might not be the common case. So some people, which I've like tested or asked this, they can't really move their little finger without also bending their ring finger, or can only move their little finger partway without their ring finger bending. Did you encounter similar problems with the testing group or the people you tested on? Do they have some kind of different anatomy in their hand? Does it influence the ultrasound imaging or the processing?
It's a great question, and yes, I encountered it during the phase of data collection. Some of the subjects reported, I think even one noticed it and asked me if that's a problem. We did not notice anything unusual in the predictions or in the consistency of the models. So I can't say that. So I can't say it was a problem, but yes, it's part of the problem of performing generalization across unseen subjects, and the fact that we are different in everything, in our muscles behavior, in our structure, in our tendons, almost in everything.
Okay, thank you.
Thank you.
I have one more question. Can I ask? I think yes.
Fine with me. I'm not sure how much time do I have.
Okay. Dean, thank you very much for your talk and for your work. And my question will be related with the tutorials. In YouTube, there's a lot of tutorials how to play pieces on piano. And usually it looks like that you see a keyboard and you see strips that fall down to keys. When I try to understand how this program works, now, for example, there is a program C Music. You just need to play something on piano, you have a MIDI file. In the same time, you can record what did you play, and it will be audio sound. And the last speeches in this program, it's a video that you need to take upstairs. How do you play? So my question is, using your technology, can you create an application that helps to see how hands go through the piano for the special pieces? Not to do video upstairs, just create it moving of the hands using your technology.
So I would like to say that yes, of course, it's one of the things that you can do. Of course, what we were not using here is that the positional information from the motion capture system. So if you would like to create such a system for piano playing, then you will also need the positional information of the hand across the piano. I believe both of them will allow what you were asking.
But you need much less degree of freedom, right? You need just, let's say, 6 DOF for the wrist, and the rest is held by the ultrasound probe. So essentially, you track the ultrasound probe itself, I guess. Its rigid location is good enough to give you that positional information.
Thank you. Thank you. Great.
Thank you.
Okay, I think this is a good place to stop unless Alex or Alon, you have final words. I think we can wrap it up.
Alex?
Yes.
So I would just like to comment that Dean, you did a great job. I think when you approached me a year or so, a year and a half ago, even 2 years ago with this idea, it was challenging, and it's going, I think eventually it's a big step towards a system that could be a service and help to many who are in need. In many ways, there's this technology is already being implemented through Haifa 3D, and Yoav is here also, and Yair. And I think it gives a big hope to those who need this kind of technology to make the operation of these limbs more trivial and more easy. And the methods, the algorithms, the deep understanding of the biomechanics that Dean did through his work here in the gate lab and the motion capture system, I think was a great contribution to this field. Thank you. Thank you, Dean.
Thank you. Thank you for the kind words.
So, Oren, I think it's now you can wrap it up.
Yeah, okay, so thank you again, Dean, and this is really great work. Have a nice rest of the day. I don't know how to wrap it up. Take care, guys.
It's a good way to wrap it up.
Thank you very much, guys.
Bye.
Bye, everyone.